Greetings and salutations and welcome to episode 4 of my video blog. I am Professor Harold C. Connolly Jr., Professor of Earth and Planetary Sciences at the City University of New York, Research Associate, American Museum of Natural History, and Mission Sample Scientist for OSIRIS-REx. I am coming to you again from the Drake Building of the University of Arizona, where the SPOC, Science Processing Operating Center of the OSIRIS-REx Sample Return Mission, is located. We are currently going through our ground system CDR, Critical Design Review, and last week we went through our SARA TAG-SAM CDR, SRC CDR in Littleton, Colorado. I was going to tape from Littleton, Colorado, but when I woke up in the mornings while I was there, it was approximately minus 18 degrees Fahrenheit. Much too cold. So the course of the day got busy, and then I got back to the hotel room in the evening, and well, I forgot and thought that the hotel room was not the best place to have a video. So critical design reviews are on the pathway to producing our spacecraft, and in the case of today, our ground system, our operation system, how we will be operating the spacecraft while it is in orbit around the asteroid Bennu. Of course, while we'll also be running it while it gets to the asteroid, and of course on Earth return, with finally the SRC, or Sample Return Capsule, landing in the Utah desert. And it's then recovered by our team and brought to the Johnson Space Center, where it is opened up in a special curation facility. And then we inspect it for the sample and spend the next 6 months of our life analyzing the sample. So it's an extremely exciting future prospect. So one of the main things that we looked at last week in our review process was the TAG-SAM, Touch and Go Sample Acquisition Mechanism, which will essentially be like a Hoover, which will suck up regolith on the surface of the asteroid. Regolith is a term that's used to define loose particulate material that is on the surface of bodies, specifically airless bodies. Over the course of billions and millions of years, the moon, of course, in the case of billions, has eroded on its surface to produce a fine regolith, a fine powder. Not like on Earth where we have soil. Soil is a specific term used, the bad truck, specific term used on Earth because it contains organics. You don't have organic material on the moon or on asteroids. In the case of asteroids, the regolith may not be billions of years old. It may only be millions of years old. Some data we have that deals with cosmic ray exposure ages, how certain isotopes are formed in grains that are on the surface of airless bodies, suggests that Itokawa, which is an asteroid that was visited by the JAXA, or Japanese Space Agency, in their Hayabusa 1 sample return mission, is only about 1 million years old or so, maybe a maximum of 8. So something's actually on the surface of the asteroid moving grains around and cycling them around so that fresh grains become exposed only for a short period of time and then mix up with all these older grains. Of course, pieces of asteroids that get delivered to Earth are called meteorites when we pick them up, and some meteorites also have very low cosmic ray exposure ages, such as the Chelyabinsk meteorite, which blasted with a big bang about 30 kilometers above, with equivalent about 500 megatons of TNT over Chelyabinsk, Russia, February of 2013. So I'm writing a paper on the potential origin of these very low cosmic ray exposure ages, or the young ages of material delivered to Earth and from Itokawa, and also referencing it to a big surprise evidence that was discovered by the Hayabusa sample mission from the particles that were returned, which is that some particles are angular but others are rounded. Rounded particles in a geologic sense indicates that you've had a high energy environment from which that particle had been moving and abrading and eroding, much like a riverbed, or in the case of sand dunes in a desert. So something was moving these particles around enough times to smooth them, begin to smooth them out, to round them. And of course, on an asteroid, you don't have moving water, you don't have moving air. what could be the mechanism producing it. Well, I'm writing this paper. I'll report back to you at some point later after it's gone through reviews and tell you what I think the major hypotheses are to explain this. And of course, OSIRIS-REx will be bringing back considerable amount of sample that will be used to test this hypothesis that I will pose to you in the future, and other hypotheses about the origin of asteroids, the evolution, geologic activity of asteroids, because asteroids were geologically active at a certain point in their histories. They have evidence of metamorphism, heating, and evidence of aqueous fluid moving through by the minerals that are contained within these meteorites. Furthermore, the dynamical history. How did an asteroid, which was once in the main belt between Mars and Jupiter, 2 to 3 astronomical units, get to become what we call a NEO, or near Earth asteroid, or an asteroid that crosses the orbit of the Earth as it's moving around the sun and eventually can impact into the Earth. So understanding that dynamical evolution from the analysis of samples is what OSIRIS-REx is also all about. So, thank you for listening to my latest episode. Stay tuned for more. Next week I'm off to Denver, Colorado again, to Littleton, so hopefully I will tape there. We're having our curation CDR in Lockheed Martin facility in Littleton, Colorado. And this traveling has gotten me out of cold, snowy New York here in beautiful, sunny Arizona. I'm so glad for it. All right, everybody. Cheers. Bye-bye. Till next time. Shimoala.